All right, was that a fun one? Yeah. Good spring days. Yeah.
And you could have come up first. You could have asked his name.
There you go.
How would know the names? The names are less
No, actually,
No, like the chemical name, like there would be some huge thing.
than that. This is way
Just
too
write,
hard.
he write that down.
So, all right, so let's look at this. So you got this racemic drug. We talked about before that if stereochemistry isn't specified, if there aren't dashes and wedges, then we assume it could be either way. So in this case, this is what we would see. And if you looked up the drug information for this structure, it would just show that structure. It wouldn't show any stereochemistry. That's not because the molecule isn't chiral. It's because it's sold as a racemate, as a mixture of both enantiomers. So I just asked you to draw both enantiomers and then label which one's which. So first thing to do then is find stereocenter. Since these are just referred to as the R or the S enantiomer, we can assume there's only one stereocenter, because otherwise it would have to be the RR or the SR or whatever. So where's the stereocenter? Did you find it?
Nope.
Nope. Right in the center, yeah. So that carbon is the stereocenter because it's got 4 different types of things connected to it. So that's where the change in stereochemistry is going to happen. So let's just redraw this and see what we find. It's my turn to draw, yeah.
That's what you get.
So that wasn't too bad. I mean, it took a little while to draw it.
Yeah, like it just was like
Well, it's right here. You can just fold your paper over and like trace it or something. Actually, that would be tougher than it sounds. You'd have to you could cut it out, like tear it out, slide it underneath, and then trace it. All right. So anyway, so this is it. So what we want to do is redraw the stereocenter so that it reflects the correct stereochemistry. Since I didn't ask you to draw a particular one. I just said draw both of them. We can just kind of pick the easier one first and then find the other one just by switching the dash and the wedge. So let's set up our priorities. We look around here. We've got oxygen, carbon, carbon, carbon. So oxygen is going to get first priority, right? So then carbon, carbon, carbon. Well, these 2 carbons then have double bonds to another carbon. And this one just has a single bond to another carbon. So that's going to probably be our lowest priority, number 4, right? So then between 2 and 3, let's see, we look at, we're looking now here versus here. So that's a tie. Those are all the same. Then we move over. This one has a carbon, 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 all carbon around it. This one has a hydrogen coming off of it. So this one's going to get a little bit higher priority. So that gets 2 and that gets 3. So that's the proper ranking of the priorities. Again, it's not about the overall size of the things attached. You go out atom by atom until you find a spot of difference, and then you see what that difference is.
So that one's R.
Well, we haven't set, it's nothing yet until we put a dash and a wedge in. So in order to make this what it is right now, kind of the easier way to do it, we put the, whoops. That's all right, we'll fix it here. We'll put the 4th one on the dash because that's like if it's a hydrogen, if it's on a dash, then you just use what's there. And then if that one's on a dash, that means one of the other ones is on a wedge. Doesn't matter which one you put. Since they're next to each other, we'll just put this one on the wedge. So now we've got 1, 2, 3. That's going around that way, so that's R. Okay. Using the magic of technology, I'll redraw it over here. And then we'll just switch these to get to the other, to get S. So at S, it would be a dash here and a wedge there. So those are the two stereoisomers. Now you didn't have to have the dash and wedge on those spots. You could put it over here, you could put it over there. Just has to have, just like any other stereocenter, two straight bonds in the plane, and then a dash and a wedge. That's always how we express the stereocenter. So there's your two enantiomers, R and S. And this has become more and more important of a distinction as we talk about in pharmaceuticals. Not just because like one might be more effective than the other. So when this was first invented, it was just sold as the racemate and it was whatever. And then it was discovered that the S was more effective than the R. And the advantage for pharmaceutical companies is they can now repatent the S by itself as a new drug and have another, whatever it is, 20 years of, or 10 years of patent exclusivity before it goes generic. So when they license this thing, I think that they're now all generic, but I think Lexapro just went off its patent like a couple of years ago. And you can now get generic escitalopram. I also like the completely not creative naming of calling it escitalopram because it's the S enantiomer, so they didn't give it like a new name, they just said S.
Okay, question.
Yeah.
I drew the mirror image,
Right?
so how would that work? Same thing?
Same thing. So if you flip this like the mirror image, then the same things would stay on the dash and the wedge.
One on the left is R, so if I
Yep.
flipped it,
Then the mirror image of that one would be S, if the whole thing is flipped.
but if it didn't show the wedges and the dashes.
Then we don't know what it is, because there's no stereochemistry shown.
Get excited for a second.
All right, so what functional groups are present here? Yeah, amine, ether. So there's amine there. This is an ether. Other functional groups, well, there's a fluorine, which is kind of functional, and then the CN, which is called a nitrile. We didn't talk about those.
Do you have to circle them on the diagram?
No. All right, and then this thing that we just kind of went over, this is a problem right from the book, from the homework in chapter 5. So to draw the mechanism, just as we did, we're going to draw that attacking the, you can redraw it or you could just use the structure. Show it attacking the hydrogen, which then leads to that carbocation. The negatively charged chlorine attaches to the carbocation. And you end up with this product.
Wait, what if the chlorine in the middle?
What if you put the chlorine in the middle?
Like on the middle line? Do you know the difference?
On the middle? Oh, no, doesn't matter. As long as it's attached to the right place. Yeah,
Can you get the extra back?
sure. You want them?
Instead of waiting.
Oh, yeah, I should have given them back before we went over.
Yeah, yeah. We should always do this. It just works out so perfectly, doesn't it?
Yeah.
Well, it took me like 3 months.
No, I'm just talking about because it's.
Oh, yeah.
Okay, let's move on. Okay, last time we went through this mechanism that was on the quiz, looked like, from what I saw, most of you have a good sense of how that works now. Then we talked a little bit about carbocation stability. So today we're just going to finish up this chapter and talk about the other types of things that you can add to alkenes. I think you mentioned, right, that it was everything seemed to be in that one column. So that's not the only things that can add to alkenes. Now we can talk about the other ones. They're all going to add from a similar mechanism, a similar idea, with slight little variations. So we'll try to find how it's similar, and then when it is different, we'll point that out too. So the next thing we'll start with is what we call addition of water. Yeah, what you were working on it. Adding water to an alkene. So water, anybody know the formula for water? Good. I should put that on the quiz. So H2O, we can think of this as an HX type compound, like HCl or HBr. H2O we can think of as HOH. Right? You did stuff in general chemistry where you thought of it as, water can be an acid and give up a hydrogen, or it can be a base and take a hydrogen. So it has some of these kinds of properties. The problem with water is it's not acidic enough to be attacked by a double bond. Double bond is not a very strong base, not a very strong nucleophile, so it doesn't want to necessarily grab that hydrogen from the water, which makes our reaction just a little bit more complicated. So does anybody know what we need to do with that water to make it work? Anybody reading ahead? So we can't draw the same exact mechanism because that hydrogen is not acidic enough. So what we have to do is use some acid to help us along. We're going to use an acid as a catalyst, meaning that we're lowering that activation energy, and also we are regenerating the acid in the process. So the acid isn't used up in this reaction, but it helps us along. The way that works is rather than simply adding water, let's take a alkene like this. So rather than simply adding water, we're going to add some acid along with it, like sulfuric acid. We need something like sulfuric acid because we know that HCl or HBr or HI, those add to alkenes on their own. So we don't want to use those as our acid catalyst. H2SO4, sulfuric acid, is a nice acid because the SO4 part is not nucleophilic, so that will not connect back to our alkene. It's just like a pure source of acid. So if we use a little acid, what we're really forming here, anybody remember from Gen Chem what happens when you put an acid in water? What kind of a compound do you form? You put a strong acid in water. Not quite. There's another species that forms. No, I'm just trying to remember back. Hydronium ion, H3O plus. Yeah, so water actually acts as a base around a strong acid and grabs a hydrogen from the acid. So you have this protonated water, which is H3O plus or hydronium. So hydronium is strong enough of an acid to get attacked by the alkene. So that's how we draw the mechanism. The rest of it looks just like what we did before. So rather than taking water, we're going to draw hydronium. And we're going to show that hydrogen getting attacked by the alkene. So where's the hydrogen going to go? You don't, but let's say we want to. Where would we put it? Yeah, so we put it over here, right? And that way we can have a cation on the tertiary center, the more stable carbocation. So then what's left over is what? What's our byproduct if this loses a H? Yeah, the OH2, or water. So this water still has two hydrogens on it. And now because we're in water, we have a neutral nucleophile. It's unlikely that you can have anything with a negative charge in acid because the acid would just connect with it and then it wouldn't be negative anymore. So in acid, in an acidic environment, the most nucleophilic thing here are those electrons on the oxygen. We know that water has a dipole. Remember that it's polar and that it's more electronegative and all that stuff. So that's the negative thing that will go to connect to the carbocation. So really it's the same mechanism as before. You know, the double bond grabs a hydrogen, and then what's left over comes in and attacks. It's just that what's left over is now neutral instead of negative. So now we've got this. What? Yeah, so that last step is for that last hydrogen to pop off and give us our final neutral product, because we usually end with a neutral product. So to do that, we need some kind of solvent, something to act as a base. So what we might do is take another equivalent of water, because we're in water here, so maybe some more H2O, and let that H2O grab one of those hydrogens off. So the end result of this is to form, just brought in some more. It's the most basic thing that is in solution, like the thing that is most likely to grab a hydrogen. So yeah, it's not something that was already existing in this reaction. It's just more of the water that was in the reaction, the solution. If we did our reaction in a different solvent, like ethanol or something, then we would put that as grabbing the hydrogen. Okay, so one thing that we form then in the product is this alcohol, and then the byproduct would be more hydronium. So the hydronium is regenerated. That's why the acid is catalytic. It's not used up in the reaction. So to sum all that up then, let's look at this compared to what we've done so far. So we have this HX thing that has been added to the alkene in the same way. Right? We didn't draw it here, but there's a hydrogen here. So just like HCl or HBr, the end result is that the H goes on one side and the X, whether it's OH, Br, or Cl, goes on the other side. And it always has the same selectivity because it has the same kind of mechanism. So the OH is going to end up on the more substituted carbon, just like the Br and the Cl. So that part's all the same. The difference is that rather than starting with the water itself, we attack hydronium ion. And then we need one extra little step at the end to get rid of one of those hydrogens and return a neutral product. Look good? So let me show you a couple ways that this can be drawn, and then you can draw the products. The way the book does it is the same way that I just did it. So they say something like this. So they put that acid catalyst over the arrow. A lot of times in organic chemistry, you'll find the reagent and the catalyst put just on the arrow. And we don't use this plus type notation like we do in more inorganic reactions or general chemistry type reactions. So I'll give you another example. You might see something that looks like this. And then a final example. Sometimes the extra acid isn't even shown because it's assumed that we know what that might be. So a lot of times, just to make it simpler, we'll just say that our reagent is hydronium. And that means the same thing. That you don't get a bottle of hydronium, but you can get a bottle of water with acid in it, and that's the same thing. So a bottle of sulfuric acid, dilute sulfuric acid, concentrated sulfuric acid, whatever, is basically hydronium ion with sulfate counterions, or hydrogen sulfate counterions. Okay, so see if you can draw the products to those three reactions, given what we just talked about.
Is it not that we don't have the hydrogen sticking out?
No, no, you don't have to draw the whole mechanism with the arrows, but you can use the mechanism to figure out the product. But if you don't need to, you can just draw what you think the product will be. Well, I'm saying that all three of those are acceptable ways to write it. Those are all the same thing. So however you like when you're writing.
They're all
But they're all basically the same thing. I mean, they're going to have slightly different products. Yeah. Yeah. I think it's unlocked, actually.
Oh, you. If you put it here. Yeah.
Oh, can I grab something from another room? Maybe have some glasses.
Oh, yeah.
Sorry. But we don't keep like a stock when I pay you some. Oh, you know what? There might be some on that actually.
There's one thing that I really think
You can only get that one. So. That's a super.
Only from those white lines.
Yeah. I know. Good flying.
There's my steps at night.
it's not, they don't have the red flag.
They went from the
Yeah, I know. Me too. I did lock nothing. Wow. Yeah. Mine's always curves. I can't watch it. Mine has the
Mine
curves.
goes like.
Mine has the curves.
This is like this. Yeah. I just like mine.
Oh my god.
That's it. Remind me to take them back because they go in that different. All right. So how are these going? You got them? I can put them up here.
She's like, "Yes, dude." Which one? Either?
Just the product. You don't have to draw the whole thing with all the arrows. Just what you get for the product.
I'll do the first one then. Oh wait, what? How do
You can
I?
use the back to erase you.
Okay, that erased the whole thing. I can't trust it. Okay. Oh, whoops, there's something else.
All right, thanks. Who wants to draw another one? And then we'll talk about them.
Thank you. Oops.
Okay, thanks. Thank you. One more? Doesn't have to be right. Just draw something. Artistic? I saw your beautiful telegram on your quiz. It looked pretty good. Since it has contributive molecules.
Oh, technology. Oh, that. Okay. Oops. How do I erase this?
The back, yeah.
Okay.
David, you put a plus next to H3O. Thank you.
Chicken scratch.
All right, what do you think about these? Yeah, this screen thing always makes people look like a third grader when they first start writing on it. So they get used to it. I used to use one that was like separate from the computer, so you had to write down here and look up there, and that was not good. Yeah, what do you think about these? They look good? Look, any issues? Right? Yeah, I think they all look good. So we made the right alcohol in each case. Main thing to notice here is just making sure that the selectivity, the region selectivity is correct, so the OH is in the right one. That's the case in all of these. In that middle one, how do you make the decision which carbon to put the OH on? You guessed?
Well, I would put it on the most substituted carbon, but.
Okay.
If I would look at it, if you even put it on the third one, it's really the same molecule.
Yeah.
It's the second one anyway.
Right. So that one, either way you go, you're making the same molecule, that middle one. And even if that weren't the case, if there isn't a distinction in stability there in the carbocations, you can't pick one. There's not going to be a major product. The product is going to be a mix of two things. So, like in that case, they're both secondary carbon. They would both be secondary carbocations. So you can't make that distinction. You make a mixture of both. All right, so you feel good with this? Maybe? All right, let's get it a little trickier. All right, so that's known as acid catalyzed hydration. The counterpart to that, acid catalyzed hydration. Hydration being adding water, just like we use it in our life. So did I write that anywhere? I did not. Let me write that down. So we'll call that 1, because there's a second way to add water that we're going to talk about now. Second type of water addition has a much, well, you'll see, hydroboration oxidation. Yeah. Give you a second to write that. At least we're skipping the oxymercuration, demercuration. That's the one we're skipping. So yeah, that's the worst. But so hydroboration oxidation, it's a 2-step reaction. The first step is a reaction called hydroboration. The second step is a reaction called oxidation. We're not going to get into the mechanism of this step. The book goes through it a little bit if you want to see what it looks like, but it's not really related to other things that we've done, so I don't think it really fits here to talk about it. We're going to just say, here's a thing, here's a reaction, here's what it looks like, here's how it works. So we're going to use a similar substrate to what we've been talking about, which is like this. And I'm going to give you the reagents over the arrow like they would be in generally like in a paper or something like that if you saw these. The book draws it this way also, so we'll be consistent with that. The first step is using this molecule called BH3, or borane or hydro, well, it's actually BH3 connected with something called THF. So that's actually a dot in the middle, because what that is, it's called an adduct of this molecule, boron with 3 hydrogens, and this molecule. It's a very unusual kind of thing. Has 2 formal charges. So it's a boron with 3 hydrogens on it, connected to an oxygen that's a part of a 5-membered ring. So this is the BH3 part, this is the THF part. And they're actually connected, so that's why it's called BH3.THF. THF stands for tetrahydrofuran. That's the name of that ring with the oxygen in it, but we'll just stick with THF. Everybody all right with this? Yeah, okay. It's a little weird, but
We need to know that,
no, actually, because we won't use it. I just wanted to show you what it is. You just need to know that it's called this thing. The second part of this reaction is using a collection of 2 molecules in water solution that you probably have seen before. Sodium hydroxide, not really a molecule, and hydrogen peroxide, which is H2O2. Sometimes you'll also see the water in there. Sometimes it's assumed that that's an aqueous solution. So I'll put that in parentheses because don't worry about whether it's there or not. This hydrogen peroxide is always generally in water solution, so it's always there. All right, let me move this out of the way so we don't get confused. The product to this is also an addition of water. So that means it's going to make an H on one side and an OH on the other side, but it has the opposite regioselectivity to the acid catalyzed hydration that we just talked about. So the product to this reaction puts the OH on the other carbon. See how that looks compared to what it would look like in the previous reaction? Let's go back and check. So that first example we did for addition of water this way, we used the same molecule. Through acid catalyzed hydration, we made this alcohol with the OH coming off that central carbon. Now, with hydroboration oxidation, we've got the OH coming off the other side of the double bond, like the wrong side of the double bond. And this is known as the Markovnikov selectivity. So that Markovnikov was that idea that the hydrogen goes to the carbon with more hydrogens, and the other part goes to the other carbon. So the anti-Markovnikov is the opposite of that. The reason this is important is because the goal of all this stuff is ultimately synthesis. Can we take a molecule that we want and actually build it from smaller molecules? And so sometimes you want the OH on this carbon, but sometimes we want it on this carbon. So we can't just say, oh, well, I guess we can't make it. And so for every time there's a dead end like that, somebody has done research and come up with a new way of getting around those rules to actually make the thing that you want to make. So if you want to put an OH on the end, you got to have a way to put an OH on the end, and this is the way to do it. The reason that it works is because boron is actually less electronegative than hydrogen. It's actually quite electropositive. It doesn't have an octet by itself. And so the double bond attacks the boron rather than attacking a hydrogen. And then the second step, that boron is kind of turned into an OH. So the boron ends up where the hydrogen would be, and then it gets turned into the OH, and that's how you get around that selectivity. So it's not like we're violating the rules of nucleophiles and electrophiles. It's just that now the electrophile is the boron, and that gets stuck to the end where the hydrogen would be. And then the other hydrogen comes in later, because a hydrogen on boron is actually going to be, hydrogen is actually more electronegative than boron. So we're not going to go through the whole mechanism, but I do want you to know that this is a possibility. And so if you want to make a molecule with an OH coming off of the end of a bond like that, this is how you do it. Questions about that other than that it looks weird? So it'll be the same kind of thing. I'll ask, here, we'll do some examples. So I'll give you a molecule like this, and I'll say, what's the product of the hydroboration oxidation? Can you draw that product?
Wait, that's not each.
Oh, thank you. Yes, that's better. All right, does anybody want to try to draw this product? So look at the previous ones we did, and then think about the opposite selectivity and draw that. Okay. Thanks.
So should we be drawing this CHM?
No. That would be necessary if we were drawing the whole mechanism with the curved arrows, but this would just be that final product. What's that final product going to be? What do you think?
You are right.
That's what you got? Yep, that looks good to me too. Nice job. Yeah. So there's really two parts of what we've been doing so far. There's this idea of mechanisms or how you get to where you're going, and then just the product. In some cases, and we'll see another one in a little while, the mechanisms are a little bit complicated, so we're just going to say, you just got to remember this is the product and this is how you make it. Other ones, we're going to go through and be able to figure out the product through looking at those arrows. All right, let's take a little break here, and then we'll come back and look at the last 2 or so reactions in the chapter. And we'll get just a little bit into the next part, the next chapter. All right, so let's start back up like 6:30. They changed the clocks? Yeah.
I mixed up the old ones. I burned my fingers, fell down the stairs, hit my head on the wall. Everything possible.
Yeah, yesterday.
Yesterday was a Monday too.
Oh, I don't know if I want to get in here. I bet those are involved.
I got a. Hey, you're here. She's here.
Having a party by yourself?
So fun. She came with love. I was crazy. This is not I.
Oh, Mountain Dew. There we go. Actually, what else weird, Mountain Dew makes me sleepy. I can drink 3 cans. And you should keep people up. I can go to sleep on 3 cans.
That's what Pepsi does.
Alright, I don't.
Caffeine, you just we just saw you, Joe. The other hallway. I just saw him.
You're walk a lap.
Yeah, we did laugh. No, you were just
I was
having
at least one. I don't want to try out there.
we ran to like the machine and back. We're just back.
No, we went to China on that. No, we went to South Korea.
That's
Oh,
it.
God, it was
Wait, no, not a cook salmon. Like really simple. How do you do it? Cook salmon. How do you do it? Grill, kill it.
inside or grill
I don't know if salmon.
or so.
I don't want to fry it. How would you fry it? I don't know how to cook it. What? I was thinking you can fry it.
He's not familiar. I was just saying, why do you need to Google?
You know,
It's a recipe.
he doesn't go to Google. Not Google. He's like, cool. I want it. I want it. It was this. How do you start?
I don't know. Go to borrow, go to the library.
He's a caveman.
Is it like a fish that's already prepared, like it's in
No, that's called that salmon to cook at home.
Oh,
That's
you got a
salmon.
fillet.
And a salmon to cook at home. I don't know how to cook it.
You don't cook it.
No, that's his dinner. Because I didn't come to eat out. Please eat out. Now he has to.
Just expensive. So maybe pieces of meat.
And fried chips and steal it. I don't know what it is. Okay, so you want to steal it.
It's hard to tell. Send it to me. Yeah, really. No, yeah. I have a lot of things. I could just get everything covered,
Yeah, minimal.
but we all.
No yelling, no swearing, nothing.
Supersonic speaking with folks.
Hey, okay, hold on. There's here. There's like
Hi, this is. Okay, so I'm gonna tell you what I'm saying. She just passed it on. Okay. All right, so you have to. Okay. So you have to take Oh, it is. Okay.
So it should exclude. So I'll take our presentation.
That's a good one. Down right now. Okay, 7 minutes ago. Bye.
It sounds crazy, but by the end, it's like, okay.
Cooking some salmon. Do you guys not have the internet at your house? Is that
He doesn't use the internet. He hates using Google. He hates it. He won't use it. He's one of those people.
well? Now he knows how to cook salmon.
I know. No, I'm hungry for salmon.
All right, we should continue.
He said they use the
I find I like scrounge around my house. Otherwise, I just find.
I think you should start.
Oh, sorry.
We should. That's all right. Did anybody else make salmon tonight?
Oh, I want salmon. I've had it.
once.
I had raw. Yeah, I had raw salmon.
I could eat like.
Well, so what was your recipe? I didn't hear. How did you?
I skillet.
For a novice.
Some people, because he's an idiot.
Did she do like a,
He
make something for
Wood
their
grill.
class?
yeah, did you make something for it? Class one day?
Yeah, we'll
I
have
think we got a pan.
only if each person takes a day, and then we alternate who cooks each
Okay,
day.
let's look with
Do
me.
that.
I'll take whatever you want. Can we do that? Can we do that?
You can bring in whatever food you want.
Carol salmon.
Yeah.
I've never had salmon.
Whoever cooking recipes, we'll relate it back to organic chemistry.
Yeah, absolutely.
There we go.
Did a lot of cooking this
It's
weekend.
all organic chemistry.
I was cooking for
Like the browning of the sugar.
12 people all weekend. Yeah, absolutely.
Do you know what happens?
Yeah.
Why?
Uh-huh.
So is it, or is it, what's going on with the sugar?
All right, well, there's two different reactions. There's two different types of reactions. There's caramelization reactions,
So
which is,
caramelization.
that's when sugar by itself is turning brown and then eventually becomes black. And that is the breakdown of the sugars becoming different kinds of things.
So just
then-
getting different functional groups.
Yeah, right. Then the more common reaction is called the Maillard reaction, which is the interaction of sugar and protein. And that's like the browning of meat or the browning of vegetables. That makes that really good, delicious flavor. That's what that is. And that is when the amino acids, the nitrogens from the proteins, connect with the functional groups on the sugars and form new kinds of compounds that are delicious. So, yeah, we can look at some of those reactions when we get into that stuff. I think we're gonna do a whole chapter on sugars, so we'll get into that. Yeah. Yeah. All right, so we got 2 more reactions of alkenes specifically. Then we'll kind of go back and look at all of them together and talk about the stereochemistry of these reactions and maybe get a little bit into the next chapter. So we have an exam next week, I believe, right? Next week, Wednesday? Yeah, so it'll be during the lab period on Wednesday. And then we'll have-
Next week.
Just do it after break? No, then you need to have a nice relaxing break where you're not
Yeah, I want that.
worried about studying for your exam. Just get it out of the way. Yeah. All right. So let's look at a couple more reactions that we are going to look at the mechanisms here. Addition of bromine or chlorine. This should not be kept. Yeah. Now, when we talk about it, we're talking about elemental bromine or chlorine, so that would be Br2 or Cl2. Based on what we've already done with HX, I'm going to ask you to predict, let's say we have this molecule again, and we react this with bromine. What do you think the product will be? If you had to guess, this down a little bit. And I gave you the hint that a lot of these reactions kind of go the same sort of way. How might you draw, what do you think the product might be? Okay, so maybe it's the opposite selectivity of the HBr and the bromine's going off to the right. What else? Like down here? Over here? Here? So like this? Another one? Okay, another possibility.
Wait, whoa.
I'm not saying this is right yet. We're just looking at the possibilities. What else do you think, maybe?
Wait, why was it?
Well, hold on. There is a problem here so far. So let's say this was the guess, and that's fine. What else is being added here that is not accounted for in this reaction? Hydrogen, right? Because if we go from this to this, even though it's not shown, we've added a hydrogen here. And that's not shown in the reagents. So what else might be happening besides that? Let's go back to, let's say we know we're not getting rid of carbons. How else might these bromines be adding to this double bond that doesn't also add a hydrogen? Yeah, one on each end. So that's actually the product here. It's just like H and something. The H adds on one side, the something adds on the other side. Br or Cl, one adds to one side, one adds to the other side. Cl would work the same. So the mechanism for this, or the way that it works, is similar but a little bit different. Make sure that I'm doing it right. Yeah. The reason we know it's a little bit different is because of the stereoselectivity, that there's actually specific stereoisomers formed in this reaction. We'll get into that in a little bit when we talk about the stereochemistry of these reactions. But let's just look at what happens in this mechanism. So it starts very much like any other mechanism. The bromines here, even though they have lone pairs, they can actually be an electrophile, and they can get attacked by the double bond this way. So that's the same kind of a step that we've been seeing in the other reactions. All right, so that's the same thing we've been doing so far. But this one's a little bit different. Because we've got this bromine with all of these electrons here, before this other bromine, this bromide ion now gets a chance to come attack, this bromine actually comes back down over here and attacks that positive charge itself, because that bromine is going to be a little bit electronegative. So we come up with this weird sort of looking thing, a three-membered ring with bromine in it. And the name for this type of a thing is a bromonium ion. It actually has a positive formal charge, if we calculated that out. And then this bromine can attack there, and those electrons can go back onto that bromine where they came from, and that leads to our final product.
So wait, what's happening there?
This bromine is connecting to the carbon through that arrow.
How is it connected? It's not a positive charge in front, so why is it connected?
That's right. So it's attracted to it because it is still, even though it's not positively charged, it is electrophilic because of the ability of this bromine to come back off of it. So yeah, and in fact, it doesn't really matter which side you draw that bromine attacking either. So you could kind of go to either one. There is a distinction, but in this case, it doesn't really matter. The reason that we draw it that way instead of just showing the bromine coming in or the bromide coming into the positive charge is that this has stereochemical significance. Let me show you what that is. I'm going to build a little model of it first, and then we'll see how that happens. We're going to make a 6-membered ring here. All right, cyclohexane. And then I'm going to build this bromonium intermediate. Now with these bonds, they don't, like we talked about before, you can't really bend them to make a cyclopropane, so I can use the curvy bonds to do it. And I'll use red to indicate that. Even the red or the curvy ones don't really like it, but we'll get close enough. All right. So when we draw that when we make a 3-membered ring on something like this, where it's attached to another ring, both of those bonds have to be on the same side, stereochemically. Like we can't have one going down and one going up, because then they wouldn't be able to reach around and connect. So they either both have to be going up or both have to be going down. So let's draw that. We'll start with this alkene. And then the book draws it in 2 separate steps. Some other books consider it to be 1 step. So I'll show you what that looks like. It's just doing 2 things together. So doing this step where it attacks one and the other one comes off, but then also showing this coming back onto the other side. So it's those 2 things we drew before, just at the same time. For our purposes, it's not really important whether those are 2 steps or 1. So what I showed you with that model is that when we form this intermediate, it has to be on the same side. It doesn't necessarily have to be up. It could be up or down. That's the same thing for this molecule. But it's got to be on the same side, which means when the second bromide ion comes in, that one has to come from the opposite side. So if this thing is up here like this is our bromonium ion sticking up, coming out toward you. That means that the other bromine that comes in has to come from the back, connect there, and then release this one to the other side. The result of that is that you end up with the trans stereoisomers. See that? One ends up forward and one ends up back. Now, it doesn't have to be that one that's back and that one that's forward. I could have put the back one on the bottom and the other one on the top. But one has to be on the top and one has to be on the bottom, if we look at it that way. Or dash and wedge is another way we talk about it. So when we draw that, what that means is that this other bromine that comes in ends up being on the other side. Or we could have made that other bromine attack on the top. Like that. So those would be the two ways. What's the relationship between those two molecules? Are they the same? Are they enantiomers? Are they different kinds of stereoisomers? What do you think? Well, yeah, are they chiral? First of all? Yeah. No, they are chiral. They are chiral. And they're enantiomers. There is a third stereoisomer that is not formed in this reaction, and that is the one where they're both up or both down. Oops. That's right. So not formed in this reaction. That makes this a stereoselective reaction. So we call this stereoselective, which means that some stereoisomers are formed and some are not. Good so far? Maybe? What? Because this mechanism does not allow for that second bromine to also come in from the top. So if they have to end up on opposite sides because of how the reaction proceeds, because of where the electrons are.
So then it can never be a cis.
Right. So you will always have trans addition with this reaction. If that's your ammonium ion on top, the other one has to come in from the back. Yeah.
Is there a situation where they can only be on the same side? Not in the, obviously not with this particular example, but in another situation?
Sure, you'd have to use different processes to do that.
Okay.
we're not going to.
But that would be stereoselective too. but it's
Right.
only
So we
be-
use a different type of stereoselective reaction that would put them on the same side. So an example of that, well, as long as you ask, let's go back a little bit. This reaction, this hydroboration oxidation, it's actually also stereoselective. Oops. Let's say we started with a chiral substrate like this. When this undergoes hydroboration oxidation, hold on, this is not a good example. Sorry. Let's just go like this. No, it's not a good example either. Let's do this one. The product from this is not just the selectivity that we have to worry about, but it's actually also the stereochemistry. So this hydroboration oxidation always puts them on the same side, the H and the OH. And the name for this is syn addition. So it's the opposite stereoselectivity from the bromine or chlorine reaction, where they would always go on the same side of the ring.
Are we gonna see a lot of addition?
Probably not. No. We'll see one more reaction that is important that does syn addition at the end of the chapter, or I guess next. Okay. So I didn't label this, but this type of stereoselectivity here is called anti or anti-addition. So anti, opposite sides, syn, same side. But the other page again. Got it? Okay. The last reaction we're going to talk about, and then we'll go back and look at one more little thing, is what we call reduction. So back in general chemistry, we learned about oxidation and reduction in terms of redox reactions, losing electrons, gaining electrons. That's also what we're talking about here But with organic compounds, it's a little more complicated to actually calculate the oxidation states. So we use a slightly different definition that still fits. You can still do the oxidation state thing with the electrons, but we find it's a little bit easier to think about it this way. We think of reduction of organic compounds as adding hydrogen. And oxidation, remove hydrogen. Now, not like acid-base reactions where there's H plus going from one to another. We're talking about removing hydrogen or adding hydrogen atoms and keeping the thing neutral or keeping it the same charge. So let me show you what that looks like. Let's say we have an alkene like this. If we do this kind of a reaction with it, kind of a somewhat unusual looking reaction, we add hydrogen, like hydrogen gas, in the presence of a metal catalyst. And this metal catalyst can be either palladium, platinum, or nickel, usually. Not all three, but usually one of those. So let's say or. You do this at high pressure in a special reactor where you put your stuff in there, you put in the metal catalyst, and then you pump it full of really high pressure hydrogen. And what happens is you add hydrogen and reduce your alkene to an alkane. When we draw in line structures, it's really easy because all you do is you just get rid of the double bonds. If we think about what's really happening here, this molecule's formula is what? 1, 2, 3, 4, 5, 6, C6, H12. And this molecule is C6, H14. So we've added 2 hydrogens, and we call that reduction. You see where those 2 hydrogens went? Went on each carbon from the double bond. What? Right. So it's not reduction in the number of hydrogens, it's reduction of the compound, like the opposite of oxidation. And so that's when we add hydrogens. And they came from this H2, from this hydrogen gas. All right. Another thing that that we should know about this is that it is often hard to control, not always, but often it's hard to control the stoichiometry. So what do I mean by that? I mean that if you have a molecule with, let's say, a few different double bonds in it, and you go to hydrogenate it, you can't really just pick one to reduce. So the whole thing is going to get reduced together. Right. Part of that, but more it's just not very selective. So even though one double bond might be a little bit more reactive than another, it's hard to not make some of them. So you might get if you really restricted the hydrogen, you just get a big mess of products. So it's not really practical to do it that way. Right, right. So usually we just kind of do it all together if we need to. Stoichiometry. That's like the measuring of the products, like making sure moles add up, that kind of thing. That's what that means.
So you got rid of 3 double bonds by adding 2 hydrogen?
Right. So technically, if we were to do this in a balanced equation, we would say that we have 3 equivalents of hydrogen here. But often in organic chemistry, we don't care about all like the accounting that we would in other classes. So a lot of times you'll just see this written like this, and it's just assumed that you have a bunch of it for everything. But you're right. You're right. You would need more equivalents of it, more molar equivalents to do that. There are a couple exceptions to this. Benzene rings are especially stable and so are usually not affected by this reaction unless you use a specific catalyst in specific conditions.
So, hexagons are?
Yeah, so the cyclohexane with the alternating double bonds, if it has the alternating double bonds, that's called benzene, and those are especially stable and won't get reduced by the hydrogen. But also things like triple bonds work with this too. We haven't talked a lot about alkyne chemistry. But alkynes will get reduced as well. So enough hydrogen got added to these first two carbons. And alkynes have straight bond angles, 180-degree bond angles. So when it gets reduced, it goes back to normal. So you still have the same number of carbons there, just with a different angle between 1, 2, 3.
Does it matter which one we use?
Oh, which metal?
Yeah.
I mean, experimentally, yes. Like, you might try some different ones when you're doing your reaction and see what works better. But for our purposes on paper, no.
Like either one of them. It's on a first thing.
Right, you can write either one. Palladium is most common. It's used as a deposited on carbon. So sometimes you'll see palladium/carbon. And it's easy to get. It's relatively easy to do. It's not expensive. Platinum's really expensive. So we usually don't use that as often. And nickel tends to be a little bit harder to work with certain substrates. So palladium is the most commonly used, but you'll see them all in different situations depending on what's needed. Yeah, why don't you get rid of these bonds? These, when you have these alternating double bonds, especially alternating in a ring like that, they're especially stable. It makes this thing that becomes really, really stable and hard to really react with. And that's, yeah, here, let me write that. So this is called benzene. So we need really strong hydrogenation conditions to do that if we wanted to do that. It's possible, but you need stronger reactants than what we have here. All right. The stereochemistry of this reaction is kind of interesting because it's not a reaction like anything else that we've seen so far in that it involves this metal. And the metal is not in solution. It's just literally like some pieces of metal. So let's look at the stereoselectivity. I'm going to kind of show you what it looks like, and then you're going to try to figure out whether it's likely to be a syn addition or an anti-addition. So here's what this looks like. The metal, I'm just going to draw like a metal surface. So let's call this our palladium surface, just a piece of metal. tiny piece of metal, but still a piece of metal. And at the molecular level, what happens is the hydrogen deposits on the surface. So the hydrogen atoms, let's give this a little space, connect to the surface of the metal. Metals have electrons, and so they can deposit here. And double bonds can also deposit to those metal surfaces. So a carbon-carbon double bond, which we know is flat, right? Planar, will sort of come down and dock onto that metal. It'll actually use those electrons from the double bond to connect to the metal. This is not a common mechanism thing, by the way, so it's just a weird picture of what's happening in this particular reaction. So we have our hydrogens stuck to the palladium, and now we have this carbon also stuck to the palladium. Via that double bond, which is now so based on that picture, do you expect that the new hydrogens will add to the double bond on the same side or on opposite sides? If you imagine the carbon stuck there on the palladium with hydrogens all around it, do you expect those hydrogens to come onto the same side or opposite sides? What do you think? Why the same? Because you picked a word and that was the one that you picked? That's fine. Anybody else have an opinion about it? What do you think? Nobody wants to guess? Are you leaning it all one way or the other, or just no idea? Could go any way. All right. Nobody wants to commit to it. You were right. It will be on the same side. So what really happens is these hydrogens kind of migrate over to these carbons. So these aren't, I shouldn't draw like that. Those aren't really reaction arrows. These hydrogens end up kind of migrating over to those carbons one at a time. And then they release the carbon from the thing. So I'm going to draw a couple arrows, meaning we have a few steps in here that we're not quite showing right. But basically, you end up with the carbon with its new hydrogens floating away from the metal surface. So if these were the new hydrogens, they'll end up on the same side. This is a syn addition, meaning same side. Let's look at a reaction where that is important. So if we hydrogenate this molecule, use platinum this time if you like. We're only going to form one stereoisomer. Which one? We're only going to form one stereoisomer. Which stereoisomer do we form? Yeah, so the hydrogens being on either the wedges or the dashes, which in this case is the same compound. So there's our methyl groups. Not, so we don't form the chiral ones like this. So those would not be formed. What? Why is it a syn addition? Because when the double bond comes down into the platinum surface, the hydrogens are all on the surface of the platinum, so they can only attach on the same side. They can't come in from the top because there's no platinum over on the top to deposit the hydrogens on. So they have to both come in from the same side once the thing is on the metal. Yeah. Good so far? All right, so we got a bunch of reactions now. We're going to look at one more version of this, and that is, well, before we get to that, this reaction is an exothermic reaction. And I don't have it on the computer here, but I'll show you on the, I'm just going to show you a table from the book. This is on page 154 for when you're following along at home. But this is an exothermic reaction. That is, heat is released when alkenes are hydrogenated because carbon-hydrogen bonds are quite stable. So what we can do is we can use the heat of hydrogenation, it's called, that is the energy that is produced in this reaction, to determine the relative stability of alkenes. And that's going to become really important in the next chapter when we're making alkenes. We're going to say that we always want to make the more stable alkenes. So take a look at some of the things about this, these numbers. So the lower the number, the less negative the number, the lower in magnitude, the less negative, the more stable the alkene is. Because what that's telling you is there's not as much energy released in hydrogenation. So that means it was more stable to start with if there wasn't as much energy released. So the least stable would be just ethylene. And what do you notice is changing here that makes this more stable, that makes an alkene more stable? Yeah, the substitution. So it's the same like the carbocations. The more other carbons that are connected, the more stable that alkene becomes. So the more carbons on there, the more stable that alkene is, the less reactive it is. And in the next chapter, we're going to look at forming alkenes. And we'll always kind of form the more stable alkenes. So that will be important when we get back to that. All right. Let's look at a slight variation of this reaction. So I mentioned let's say we have this alkyne. And I mentioned that if we simply hydrogenate this the way we've been doing the other stuff, we'll just get rid of that triple bond completely and completely hydrogenate it. So this molecule would be 2-butyne, and then this is butane. Yeah, right? That is butane. It's got a triple bond that starts at carbon number 2. ene is double bond, ine is triple bond. So we got 2-butane. But what if, again, from a synthetic standpoint, maybe we don't want to do that. Maybe we want to make a double bond out of a triple bond. So there should be a way to go from 2-butane to 2-butene. And in fact, there is. Let me make sure the book does it the way that I want to do it. They don't even really talk about it. Okay. So the book just calls it hydrogen with the Lindlar catalyst. And that's correct. Lindlar catalyst. That's correct. So that's a way to do that. What that is, it's actually still palladium, but with a couple other molecules, barium sulfite and quinine. And the way we refer to this is that this is a poisoned catalyst. That doesn't mean that it's poisonous for you, although it probably is. Quinine is an organic molecule. Now we don't need to go through and go into the structure, but it's actually made in the bark of a tree. It is what is the main. We eat it. It's the main flavoring in tonic water. If you ever have seen tonic water, it has like a yellow label. It's used in drinks. It's an anti-malarial molecule. So sometimes people used to take, still do in some cases, take quinine for malaria, although it's not as effective as it used to be. But what it does is it messes with the electrons a little bit. So what it effectively poisons the palladium catalyst. It makes it less strong, makes it weaker, so it can no longer react with double bonds. It can only react with triple bonds. The regular old palladium, we know, reacts with triple bonds and double bonds all at once. So if we put this other stuff in there, it can no longer react with double bonds, and now it's stuck and it gets stuck at the double bond. Because it's still a solid-based, metal-based catalyst, we still have that cis selectivity, that syn selectivity, but now that just means that the hydrogens are going to be on the same side of a double bond. Everybody feel good about this? So let's do a quick review of the things that we have been able to do now to alkenes. This is a good thing that you might want to write yourself as you're reviewing for the exam. So let's do an asymmetric alkene like this in a ring and review the various types of reactions that we've talked about. So what's one thing that we can do to this? Somebody give me one. Okay, so yeah, the thing we just did was the reduction. Okay, what's another one? Yeah, we could add water. So water in the presence of acid gets us this kind of a product. Hydroboration. Yeah, hydroboration is going to give us the opposite of the regular hydration. And that's going to give us the syn addition, right? So we're on the same side. It's actually going to give us both enantiomers. I should also note, I don't think we really talked about this. It is important that these are labeled 1, 2. What that means is that these are done in successive steps in the lab. So you do the first reaction, stir it for a while, whatever you're supposed to do with it, and then you put in the stuff for the second part. You don't necessarily isolate it in between. You don't like crystallize it or anything like that, but you do one thing, wait till it's done, then do the other. If you don't have those numbers, that means that everything under those arrows, you just get dumped in all at the same time. So that's an important distinction, because if you dumped all this stuff in at the same time, it wouldn't do anything. You have to put in the borane and the THF first, and then you can work it up with the sodium hydroxide peroxide. All right, so I think there's 2 more that we've still got to put in here. You gonna remember them? One of them was on the quiz.
It's the one we just looked at. Is the hydrogen keep the bond to the chlorine and regular?
Yeah,
Reaction.
the regular, the usual. So HBr or HCl or HI. Also, I'm going to edit this one. Just even though this is not a chiral molecule, we should note that that would be a syn addition. Doesn't actually matter in this case, but that those things go on the same side. And then the last one is Br2 or Cl2, which adds both of them with anti-selectivity.
Okay, so then the one that we call the regular one,
Mhm.
is it always for B, BR, CL, I?
Yes.
Regular reaction?
So this could be HCl or HI. This one could be or Cl2. And give us chlorine, obviously, instead of bromine.
Okay, I have a question.
Yeah.
Really, H2 over helium, do we have like the hydrogen and then branch out?
No, it depends on the molecule. So in this case, it doesn't make sense to do it that way. I just did it because I wanted to show that. So this would really just be like that. But in some molecules, it's going to be important that we have the syn selectivity. So depends on the molecule. If there's a chirality thing there, then you've got to put that. You got to show that. If not, then it doesn't matter.
What's the other synergistic one?
This one. So this one has no selectivity because the bromine can go on either side and it's done as separate steps. The carbocation is flat. So there is no stereo. So once you form a carbocation, you lose the stereoselectivity.
And that's, the carbocation is only for the HBr.
Nope, this one too. Right, the addition of water.
So those two are carbocations,
Right.
and when they're carbocation, it's because there's no stereoselectivity.
Yeah, that you lose the stereoselectivity at the carbocation. So then this one is syn addition. This one is syn addition, and this is anti. So this becomes important, or will become important, as we build our library of reactions that we know. We can start talking about how to turn something into something else. So I have this molecule, I want to make this one. What sequence of reactions am I going to take to do that transformation? That will kind of be the overall goal of what we're doing as we get more and more reactions. Okay. So we'll stop there. There is one more little section that we didn't quite get to about rearrangements. What happens when sometimes the molecule can rearrange in the middle of the reaction. That is that's section 5.4. So go through that and let me know if you have any issues with it. Other than that, this will be where we stop for the exam next week. So we won't.
What's that section?
5.4. So we won't have any of chapter 7 on the exam next week.
So what chapter, is everything covered between chapter 4 and chapter 4?
Yeah, so 1 through 6 will be all covered on the exam. Because 6 is stereochemistry, so that was one that we did earlier. Yeah. Yeah, everything's cumulative. Although really, it can't not be, because you have to be able to draw structures, you have to be able to, like everything comes from something earlier. We can't talk about anti-addition if we don't know what stereochemistry is, so it all kind of goes together. That doesn't mean I'm going to pick obscure facts out of chapter 1 or something, but you'll need a lot of the stuff in there. So this exam will have some naming, stereochemistry, reactions primarily, functional groups, mechanisms, all that stuff we've been doing.
Will you have a word bank like you did today on the quiz for the types of functional groups?
Probably not. I would probably ask that question as just find the functional groups in this molecule.
And then on Monday, are we going to do review then, or are we live?
No, we're going to get, actually, let's do this. Why don't we do another quiz on Monday? Just because otherwise this new material won't be quizzed until the exam. So we'll do another quiz on the stuff we did today on Monday. And then, so then that makes you get ready for the exam a little bit sooner. So you have a couple of extra days. And then, so we'll do that quiz, and then we'll get into chapter 7, because we're actually like at least a chapter or two behind from our schedule, but we'll get there. Right, no lab next week. This week we do have lab on Wednesday. It's supposed to be nice and warm, so don't forget to dress lab appropriately. Shoes and stuff, pants. Probably won't be shorts weather, but it might be shoe, non-lab shoe weather.